Okay. So there's a lot of parts to this problem, but hopefully they don't take too long. So the first problem says, how many stages does this distillation column have? So I'm going to show two different ways of doing it, and then you guys are going to tell me which one's right. So we're going to count stages off the equilibrium line, which is this curvy graph. Or are we going to count the stages off the operating line, which are these lines right here? So which option did you guys go with? Equilibrium lines? Good. Because we're counting the number of equilibrium stages. So it makes sense that we're going to read these points off of the equilibrium line. All right, second part. What is the composition of the acetonitrile-rich product? All right, so obviously we're going to have one stream coming off the top of the column, one stream coming off the bottom of the column. So this product is either going to be located here or here. And which one is more rich in acetonitrile? It's pretty obvious to tell it's going to be the one that's farther right. So it's going to come off the top of the column as a distillate. Just read it straight down, 66 mole percent. Well, so the other one must be more rich in water, and that's coming off at the other point. 2 mole percent acetonitrile. So almost pure water off the bottom. All right, so part D. Now we want to know the compositions of the streams leaving the feed stage. So most of you found that the feed stage is where this corner happens, so it's dealing with this triangle here. All right, so there's two approaches I'm going to use. We know that the feed point is the intersection of the two operating lines, right? The feed changes the liquid and vapor flow rates, so it causes this kink operating lines. So we just look at this point and read off the compositions. And this would be liquid, and this would be vapor. Or we can say, well, in the feed stage, we know that liquid-vapor equilibrium is going to be achieved. So we would look on the equilibrium curve to read our liquid and vapor compositions. Which did you guys do? Equilibrium. And it's by the same reason why we counted stages off of the equilibrium curves, because at each point, equilibrium is achieved. So at the feed stage, the two streams leaving are at equilibrium. So we have a vapor of 52 mole percent and a liquid of 9 mole percent acetonitrile. All right, what is the ratio of liquid to vapor flow rates in the rectifying section? So there's two sections in the distillation column. The rectifying section is going to be the top one, and the stripping section is going to be the bottom one. So which one of these points is at the top of the column? Yeah.
The higher section of the graph.
And why do you say that?
Because the acetonitrile is coming off the top of the column because there's a lower boiling point.
Exactly. The acetonitrile is more volatile, so it's going to come out as a vapor as opposed to a liquid. So we're going to look for the acetonitrile rich stream. So that means that this line must be our operating line for the rectifying section. Well, operating lines have a slope of L over V, so if we calculate the slope of this line, we can get the ratio of liquid to vapor. And that's pretty easy, rise over run. So we get about twice as much vapor as liquid. All right, switching graphs. Now we're on a temperature composition graph. So like should have said in his previous presentation, this phase here at low temperatures is going to have to be liquid. At high temperatures, we want vapor. That should make sense. And in between, we'll have liquid-vapor equilibriums in each of these pockets. So if we start at a liquid here and go up, we'll hit this curve, which will be the bubble point of the mixture. If we start at a vapor and go down in temperature, we'll hit this curve, which will be the dew point of the mixture. And at this point here, like we've said, is the azeotrope, where we're not going to get any more separation. If we boil or condense, we're still going to get the same composition in the liquid and vapor, so no separation is happening. Nothing will change in the mixture if we operate at that point. Okay, so we want to preheat our feed stream to be at the same temperature as the feed conditions that we found earlier of the column. So the conditions we found earlier were the vapor at 52 mole percent, and the liquid had 9 mole percent. So we just sweep down this curve until we find a temperature that satisfies both of these points. You can see we have 52% here in the vapor, 9% here in the liquid, and so that's a temperature of about 82.5. And then now if we want to find the ratio of liquid to vapor in this stream, lots of simple lever rule, what we've been doing before. We know we're feeding in 20 mole percent, so that's where we put our fulcrum. And you guys have done this calculation a number of times. L to V is going to be the vapor arm over the liquid arm, which equal 2.9. Any questions? All right, go ahead and start working on the next one.